My last video got cut off prematurely. It was technical issues with my camera here. So I'm just going to pick up where I left off in that last video. Here, again, we have cosine of theta equals negative 7/10, tangent of theta equals negative root 51 over 7, and we're asked to find the other four trig functions evaluated at theta. And what I was starting to say in that last video was that we have, there's more than one approach that works here, but I want to try and use the Pythagorean identities to come up with an answer. So what I'm going to do here is first try and find the easy trig functions to find. So cosine of theta and tangent of theta, we know those. That would actually imply that secant of theta and cotangent of theta are very easy to find, because all I need to do is take reciprocals of each one of these. So secant of theta should be the reciprocal of cosine of theta, which would be negative 10/7. Nothing really to do there except flip the fraction over. What about cotangent of theta? Well, cotangent of theta would be the reciprocal of tangent of theta, negative 7 over root 51. And I do want to rationalize. That's easy to do. Negative 7 root 51 over 51. So I have a couple of answers. Okay. What's left to find, though? I need sine of theta and I need cosecant of theta. Well, I can find either of those using, one or the other Pythagorean identity. Let's use the one that we're familiar with. Cosine squared plus sine squared equals 1. Cosine squared of theta plus sine squared of theta equals 1. I could also use cotangent squared of theta plus 1 equals cosecant squared of theta. That's one of the alternative versions that we just found, except I'm looking at cotangent and it looks a little bit more cumbersome to work with than cosine does. So cosine of theta is negative 7/10. I'm squaring that, plus sine squared of theta should equal 1. What is negative 7/10 squared? It's 49 over 100. That's going to equal 1. If I were to get common denominators and subtract 49 over 100 from both sides, I'm going to get sine squared of theta equals 51 over 100. And here's where we take that square root. Sine of theta equals, remember this is plus or minus root 51 over 10. That's the square root of 51 over 100. And as we've seen in a similar example from a previous section, sine of theta cannot be both a positive and a negative number at the same time. It has to be one or the other. So that means we need some way of determining which of these plus or minus here is the correct part of that answer. And the way that we do that is we make a determination on which quadrant our function lives in. Okay, so remember we had this mnemonic device. I'll return to that. Right here, all students take calculus. Now looking at my given information, we're told that cosine and tangent are both negative numbers. If you notice, that rules out quadrants 1, 3, and 4. In quadrant 1, all functions should be positive. Here, tangent should be positive. Here, cosine should be positive. But if both cosine and tangent are negative, that must mean we're in quadrant 2. Okay? So I'm going to make a little note of that. This information means that we are in quadrant 2, Q2 for quadrant 2. I know that in quadrant 2, the sine function is always positive. So if sine of theta, if this theta is the same theta that we're talking about up here, which it is, then I must be talking about the positive solution to this. So that means sine of theta is equal to positive root 51 over 10. One left to go. Cosecant of theta. Well, I can find cosecant of theta pretty easily now because cosecant is the reciprocal of sine. So I take cosecant of theta, flip it over, or flip my sine over, 10 over root 51, and then rationalize. 10 root 51 over 51. And there's all four of my solutions. Okay? Just a little bit left to cover here. Trigonometric functions, one of the things that makes them really useful in applications is actually not the fact that they have anything to do with angles. We'll see this a little bit more clearly in Chapter 8, but one of the most important properties of our trig functions is that they are periodic. And what that means is that they have a repetitive behavior. Put a little bit more mathematically, the definition of a periodic function is a function f of x such that f of x is equal to f of x plus p for every x in the domain of f and for some number p. And the smallest possible value of p that satisfies this is what we call the period of f. I don't expect anybody to look at that definition and have anything close to an intuitive understanding of what that means. So I'm going to illustrate this using what we know about our trig functions. Okay, so let's suppose we have our unit circle right here. Okay? And let's suppose we're talking about some angle t, which determines some point x, y right here. Okay? 4 out of our 6 trig functions have a period of 2 pi radians. So what that means, let's look at the sine function, for example. Sine of t is equal to, let me write that differently. Sine of t is equal to sine of t plus 2 pi for every t, for every angle that I can plug in there. Compare this to our definition up here. The p that's being shown here is 2 pi. That's the period of the sine function. And what does that literally mean? Well, notice, first of all, in this case, sine of t is equal to y. By definition, it's the y coordinate of that point on our unit circle. What is sine of t plus 2 pi? Well, t plus 2 pi, remember, that's an angle. We plug angles into our sine function. But what does that angle look like on the unit circle? Well, if I'm already at angle t, and if I add 2 pi to that, we know that that creates a full revolution around the unit circle coming back to the angle t. That would be t plus 2 pi right there. But because we added one full revolution, all that did was take us back to the same terminal side, which determines the same point on the unit circle, which means the sine should still be y, same value. So these two things are equal to each other. That's what that means, okay? And down here, you can see all 6 of our periodic identities listed. Here's the one for sine that we just looked at. However, you'll notice that the tangent and the cotangent function, instead of having a 2 pi in there the way that these 4 do, they have a pi in there. Now, why is that? Well, the tangent and cotangent functions have a smaller period than the sine and cosine, cosecant, and secant functions do. And the reason for that, if we investigate what happens when you add pi to this angle t, pi is a half rotation, or a 180-degree rotation, which means if I'm already at angle, let's take a look at tangent now. Tangent of t equals, if I were to do a rotation of pi from my angle t, so that my angle looks like t plus pi, it's going to take me to this other this segment right here in the 3rd quadrant for this example. Okay, so this angle right here is t plus pi. Now, how does this point compare to this point? Well, notice there's an apparent symmetry here between these 2 right triangles, and the way that symmetry plays out is that we recognize that the height of both triangles is the same, but one is above the x-axis and the other goes below the x-axis. Well, it's the y-coordinate of this point that determines that height. So what that means is that instead of having y as my y-coordinate, I have negative y. And a similar argument could be made to show that that's negative x. The symmetry here implies that if this is xy, then this would be negative x, negative y. Tangent of t, we know, is y over x from this point, y over x. What is tangent of t plus pi? Well, now t plus pi takes us to this point on the unit circle. Tangent is the y-coordinate, negative y, over the x-coordinate, negative x. But here the negatives cancel, and I get y over x. Same thing in both cases, so that these two are equal to each other. Same argument can be made for cotangent as well. So that's where we get these things called the periodic identities. Okay? And again, we're introducing this here, but this becomes much more important in Chapter 8 when it comes to actually graphing our trigonometric functions. So we're going to be using this much more once we get to that point. Okay, that's it for Chapter 7.